See, coolant is the most important part of a nuclear reactor. Coolant does what it stands for, like it cools the reactor, but also it transfers the heat. It takes the heat out of the reactor core and gives it over time to the turbine. So if the heat stays over there, that is what we call meltdown. So that was the problem in Fukushima. The pump that was supposed to wipe out the water, heated water from the inside of the reactor core did not work because the plant no longer had a power supply and the generator was not able to work. And because of that, the water that was in there as a coolant stayed over there and over time heated up into steam, and that is what we call a steam explosion. And over time there was a hydrogen explosion, because at very high temperatures these hydrogens will split as well, and this hydrogen, as you know, is very explosive. Got the point? So the coolant plays a very important role, and almost any disaster that you are going to see related to nuclear power plant, there was some problem or the other with coolant, because if coolant was working properly there would not be a meltdown as well. You get the point? Because it will be taking out all the energy. But most of the time what happens in a nuclear power plant, if there's a disaster, there's not like 12 of them that we can discuss, but what happens is that because the coolant cannot flow, the core melts down. And core meltdown is a dangerous thing, because now it's all radioactive and it will pass through almost anything that you can think of, because the temperature inside the reactor keeps on increasing. Now you will be thinking that why can't we just switch off the reactor and push down all the control rods, and it will absorb all the neutrons and the reactor has just stopped producing any power now. Now that makes a lot of sense, doesn't it? But there's something that we call decay heat, and decay heat comes because of the small reactions that keeps on happening. So you can press the button and drop all the control rod, and what will happen is that the reactor will now become subcritical and over time will shut down. But that overtime is the important part, because it will take some time to completely shut down, and that time it will keep on creating heat, and that heat is called decay heat, which has to be wiped away. So what happens in a case scenario like, let us say, Fukushima, where earthquake has happened? What if that earthquake knocks off the power grid? So that power grid will be providing power to run the pumps, right? So now if that is out of the picture, how will that pump run to keep on rotating the coolant? So the second answer is the generator. So the generator will run the pump, and then pump will remove all the decay heat while the reactor is shutting down. But then again, what happened in Fukushima is that a lot of generators were downstairs, and because of the tsunami, the generator rooms were flooded. And because of that, generators did not work. So some of the backup generators worked, but over time they also started malfunctioning, and ultimately it turned into a disaster that we all know of. Now, if you talk about what happened in Chernobyl, I'm going to be discussing this in much more detail over time, but what happened in Chernobyl, I'm pretty sure a lot of you guys watched the TV series. So they were trying to see if we shut down the reactor all of a sudden, will the still spinning turbine will be able to pump the coolant. So the generator at that time used to take some amount of time to start up, right? So how will you run the coolant in the time where you have turned off the reactor and the generator is still starting up? So their idea was that the turbine, which was spinning at high velocity, is going to continue to spin, although with a retardation, that is decrease in angular velocity, is going to slow down over time. But they thought that it will continue on spinning for some amount of time, and that can be transferred to the pump. So the pump will be able to cool down the reactor until the generator completely kicks in. But the problem was completely different, the xenon poisoning thing, which I'm going to be discussing later. But you understand how important a coolant is, right? So even in a reactor where you do not need to slow down neutrons, for example a plutonium based reactors, you are definitely going to need coolant. So